So continuing on, here we've got vertices of this many degree. So I can tell by adding those degrees up, right, that there's a total degree of 16. Total degree of 16. And we know that that's always equal to 2 times the number of edges. And so that must mean the number of edges is 8. So can we have a graph that has this degree, or these degrees, I should say. So if I add these up, that gives me a total degree of 9, and that doesn't work, right? Can't have an odd degree. So in a group of 9 people, can we be friends with exactly 5 others? So what that means is each of those 9 people are going to shake hands with 5 others. And so that gives us a total degree of 45. Again, that's odd, not possible. Okay, so those were the missing problems from section 1. So in the section 2, I gave this one for you to do. So remember Euler, that's how you say his name, Euler, you get every edge exactly once, and you're allowed to duplicate vertices. So if I want to get all of these edges, I could start at V0 and then go over on the road of E1 and get to V1, and then go back on E2 to get to V sub 0, and then go back on E3 to get to V1, and then go back on E4 to get to V0. So it's a circuit because I start and end at the same place. And so then that is an Euler circuit. So remember, every edge exactly once, you can repeat the vertices. So Euler has edges repeated. Okay, so then here, is it possible? So here's a big definition I want to make sure you know. If and only if. An Euler circuit is only possible if the graph is connected and every vertex has an even degree. Oh no, right here, I can see that that's a degree 3. And so since that's degree 3, no Euler circuit. No E circuit. Okay, so what about, excuse me, this one? I see each vertex has degree 2, but wait a second. Can you see that it's not connected? Right? So these 2 triangles are on top of each other, so it is not connected, and so that means that there's no Euler circuit available. Okay, so then I had you do those. So finding out whether there's a Hamilton circuit. So Hamilton is the salesman, and he doesn't want to go to cities more than once, right? So every vertex exactly once. So we want to make sure that we have every vertex of degree 2. So looking at this one, is it possible to eliminate edges? That's what we're trying to do, to find out if I can make every vertex of degree 2. Well, if I eliminate that edge, well, this one's still going to have a degree 2, and then here, so it's not going to be possible for me to keep it connected. I can't take that one out, and I've got these ones. If I take those 2 out to make this a degree 2, this vertex or this city is going to be all on its own, and so it cannot be done. And so this is more of a, you can't find like exactly what it is, but you can just, it cannot be done because edges eliminated, right? Because edges are the roads that we don't want to do, doesn't give a connected graph. Give connected. And remember, we're trying to make a circuit, right? Where he starts at one end and then finishes up, have every city of degree 2. Okay, so here's another one. So I've got a connected graph. Okay, that's good, right? If I'm going to have an Euler circuit, it's got to be connected. It has 5 vertices, and here are the degrees of the vertices. Wait a minute, I've got 2 vertices of degree 3. So all the vertices must have an even degree. So this cannot happen. No Euler circuit. All right. How about this one? It's got a graph, 5 vertices. Okay, so we've got all even degrees. Is it possible to have an Euler circuit? Oh, but what was that definition again? It said it had to be connected. And so this doesn't say connected, so the answer would be no, not necessarily. So it could be connected, but it doesn't say it has to be, so that doesn't preclude that you're going to have a circuit. All right, so let's look at this one. So will this have an Euler circuit? So I want to be able to go around, get every edge exactly once, right? And I can repeat vertices. So I'll just start here at V2. And this is what you'll do when you want to write your homework answers. And then you'll say, okay, I'm going to go to V3. And then I'll go to V4. And then I'll go to V5, right? So I've gone here, here, here. I'll just go up to this one. And then I'll go up to V2 again. And then I'm just going to go back down, right? I'm going to go back down to V5, back to V4, and then go to V1, and then back to V2. So back, down, down, over here, over here. All right. Let's have a look at this one here. Does this one have an Euler circuit? So the first thing I like to do is just scan through to see, are there any vertices of odd degree? Yep, I see a couple of them, right? So since there's an odd degree vertex, there's no Euler circuit. Okay, so Hamilton circuit. So Hamilton is every edge every vertex exactly once, right? So see if we can do this. So I'm going to start here at the V naught. And I'm just going to draw this one so just so I can see. So there's my V1, and then I'll see if I come down to the V2, get to that city, and then I'll go out to the V3, and then down to the V4, and then let's go out to the V5, and then, I think this could be done, right? So then I'll go up to the V6, and then I'll back up here. So I hit every vertex exactly once, and I made a circuit. This one here, if I start taking off edges so that this degree is 2, well, that's not going to make it connected, right? So taking those edges off or taking those edges off. So this is not possible. So again, if you can't make every vertex of degree 2 by eliminating edges, it's not possible to make a Hamilton circuit.